So in this class, we shall start with molecular orbital theory in coordination complexes. Now, before moving into the octahedral complexes straight away, let us first consider a simple complex of type ML. So let us consider a simple complex of type ML, for example, where M is the metal ion. Now this metal, let us consider that this metal contains two orbitals A1 and A2, which are degenerate. They have the same energy. Okay, this is an assumption, of course. We are assuming that the metal contains two degenerate set of orbitals A1 and A2, like this. Say this is, for example, A1 and this is A2. Okay, these are two degenerate set of orbitals having the same energy. And considering this ligand to approach the metal and the ligand, the orbital of the ligand, these are the atomic orbitals, of course. The atomic orbitals of the ligand, which should be involved, say if the ligand approaches from this side, then say this is the ligand, this is the atomic orbital of the ligand B, which should be involved in bond formation. And suppose let this metal contains one electron. Okay, and the ligand, see, the ligand will always contain a pair of electrons. That means the metal contains one electron and the ligand contains a pair of electron in this orbital. So if we think in terms of molecular orbital theory, how should we proceed? See, this is the if we consider this energy level, so this is the metal and it has two degenerate set of orbitals A1 and A2. These are degenerate, they are of same energy. And the ligand on the other side, the orbital B, since the donor centers, they are more electronegative, they have greater orbital electronegativity. So that's why this orbital, the orbital of the ligand, it should be of lower energy, এটার এনার্জিটা কম থাকবে compared to this. Okay, so this contains a pair of electron and there is an electron in the degenerate set of orbitals. This electron can be present either in A1 or A2. Now if we think in terms of molecular orbital theory, see, when the ligand is approaching the metal center, what will happen? These two orbitals, which one? These two orbitals, they will interact to form a bonding and an anti-bonding molecular orbital, isn't it? So the approaching ligand, this A1 and B will interact to form, A1 and B will interact to form a BMO. Say this is the BMO, and an anti-bonding molecular orbital, say this is the ABMO. So this is, let us say, Chi bonding, and let us say this is Chi star or Chi anti-bonding. Okay, and this A2, now this A2, what will happen? A2 is not interacting, so this A2 will remain as non-bonding. So this will be Chi non-bonding. So A2 will be transformed to Chi non-bonding, isn't it? So this is as per molecular orbital theory. Now, if you look into these molecular orbitals, the nature of these molecular orbitals, so this will be of more ligand character because it is closer to the ligand, isn't it? Now this one, will be, this will be of more metal character. It is closer to the metal. And also this will be of practically 100% metal character. Isn't it? Now, if you consider these molecular orbitals, see these are the atomic orbitals, AOs. And if you look into the molecular orbitals, see there are 3 electrons in total. These 2 and 1, there are 3 electrons. So a 1, 2, and this is the third electron should be placed in the shy non-bonding molecular orbital. Now, if we want to compare this with crystal field theory, see from molecular orbital approach, we are getting, for the simplified ML complex, we are getting this molecular orbital energy level diagram. Now, if we think in terms of crystal field theory, see this is the metal, these are the 2 orbitals, A1 and A2. Now, as per crystal field theory, this ligand, I should name this L as not B. This ligand L is a point charge or a point dipole as per crystal field theory. So when we are considering crystal field theory, as per crystal field theory, you know that this will behave either as a point charge or a point dipole. So what will happen when this point charge or point dipole, when it will approach the metal center? So this point charge, this point charge or point dipole will interact with A1 to a greater extent. So what does it mean? See, if we think in terms of crystal field theory, we have to consider the orbitals of the metal which are degenerate. Degenerate set of metal orbitals A1 and A2. The orbitals of the ligand should be neglected. Now what happens? Since this ligand is approaching A1, this A1 will interact to a greater extent. So this A1 will be energized and A2 will be stabilized to a similar extent. And in crystal field theory, we say that this gap is delta, whether it is del O or del T. And these orbitals, these are the orbitals of the metal only, isn't it? So it is the energy gap between the orbitals of the metal. Now, if you compare this one, if you compare these two figures carefully, see if you look at these two figures, this one, this energy level diagram, and this one. If you compare these two energy level diagrams, look carefully. This is, see, this is the orbital of metal, metal orbital of metal character. In the MO energy level diagram, these two are of metal character. So we can say that this gap, between the non-bonding and the anti-bonding, it can be considered as delta, because this is the gap between the two orbitals of metal character. Since these two are metal, these two are of also metal character. And this orbital, this is of ligand character. Naturally, there is an additional information, that is the orbital. This is the orbital which is of ligand character. And you see this pair of electron, must have come from the ligand side. So the ligand donates electron pair to the metal center. So there is a donation of electron density from the ligand side. তো আমরা যে বলছি যে এই মেটালের সঙ্গে লাইগ্যান্ডের বন্ড হচ্ছে, so if we think only in terms of sigma bond, there is electron donation from the ligand side. So except for this, we are getting we are getting, see, the same result. This gap is delta and this gap is also delta. That means molecular orbital theory, this one, and crystal field theory, you see, they are giving same results, similar results, except for the additional information regarding this orbital. So that is why by using crystal field theory, we have obtained several good results. I mean, crystal field theory can explain a lot of things, a lot of properties for the complexes. But you can well understand crystal field theory, it cannot be a reality. This theory is absurd because the ligands are considered as point charges or point dipole. So that is why the molecular orbital theory, where we have constructed molecular orbitals by combining suitable atomic orbitals of the ligand and metal. Okay, so this is more meaningful. So with this basic idea, let us now move forward to construct the molecular orbitals for complexes, for octahedral complexes. Okay, for octahedral complexes, so if you want to draw the molecular orbitals for octahedral complexes, say of type ML6, say Z, whether it is plus or minus, whatever it is. It can be 0 also, it can be a neutral complex. Now, for example, say CO F6, 3 minus, whatever it is, or cobalt 3 আছে. So these type of complexes, octahedral complexes. Now the orbitals of the metal, which should be involved in bonding, they should be the outer orbital. So if it is a 3D metal, for example, then the outer orbitals will be 3D, 4s, 4p, isn't it? Because these are the outer orbitals, 3D, 4s, so they are involved in bonding. And we have to consider the outer 4p orbitals also. So the orbitals which, if you generalize this, the orbitals which should be involved are ns, npx, npy, npz, and n minus 1 dxy, n minus 1 dyz, dxz, dx square minus y square, and dz square. So these are the orbitals. These are the orbitals of the metals. They should be involved in bonding. So you can well understand there are 9 atomic orbitals. 9 atomic orbitals of metal, of the metal center. Now these 9 atomic orbitals, these 9 atomic orbitals, they are actually, um, they can be considered to be, but they can be transformed to 4 symmetric groups. The 9 atomic orbitals of metal centers may be transformed to 4 symmetry groups. In terms of their symmetry, okay, they can be classified into 4. Nota different na kore, we are classifying these 9 orbitals into 4. How? See, s orbital, the s orbital, that means this one, it will transform, s orbital will transform to a1g, a1g. That means it is non-degenerate. Obviously a1g একটাই হচ্ছে non-degenerate. Now px, py, pz, they will transform into t1u. So this is threefold degenerate or triply degenerate, threefold degenerate. Now, see, they are of similar symmetry. Px, Py, Pz. You can well understand they are of similar symmetry. Now, this s orbital, এটার নামটা হচ্ছে A1G. You have to remember this at your level. Uh, Now, the dxy, dyz, and dxz orbitals, they will transform into T2G. You know this T2G already. So once again, this is threefold degenerate, and dx square minus y square and dz square. These two orbitals, they can be transformed to EG. So this is a doubly degenerate, twofold degenerate, twofold degenerate. That means these 9 orbitals, instead of naming these orbitals, naming these 9 orbitals, we shall now consider A1G. আমরা কি বলবো? A1G, T1U, T2G, and EG. So the atomic orbitals of the metal, the 9 atomic orbitals of the metal centers, they are transformed to 4 symmetric groups. Okay? Now what next? See, in molecular orbital theory, just if you can recollect what has to be done. In molecular orbital theory, if there are more than one, say if it is of the type, say AB2 molecule, so there, if this be the central atom, these are the terminal atoms. If there are more than one atoms, then what has to be done? We have to construct group orbitals. The group orbitals of these two were constructed, for example, in water molecule or BeH2, BeF2. You'll find that group orbitals are usually constructed. So in this case also, we have to consider group orbitals having matching symmetry with these 4. Okay, so what we say is construction of ligand group orbital. So এই group orbitals গুলোকে আমরা বলছি ligand group orbitals. So construction of ligand group orbitals. Construction of ligand group orbitals, or LGO. Construction of ligand group orbitals having matching symmetry, having matching symmetry with the 4 orbitals, of metal. So we have to construct these. So if you look at this octahedral complex, now the question is how to construct the group orbitals. See, if you look at these octahedral complexes carefully, say suppose this is the x-axis, this is the y-axis, and this is the z-axis. Okay, now say if for example, if I say water is the ligand, say let us consider a complex FeH2O whole 6 3 plus, for example, whatever it is. Say when you consider water to be the ligand, so how this water molecule is donating electron density? It is donating electron density through this lone pair. The lone pair of orbitals, they should be involved in donation of electron density. Now these lone pairs, you know that they are present in sp3 hybrid orbitals, and the actual shape of the orbitals, you know, it's more like this. ধরো এটাকে যদি পজিটিভ ধরি, এটাকে যদি নেগেটিভ ধরি, it's more like this, sp3 hybrid orbitals. So if you consider these 6 water molecules, so the sp3 hybrid orbitals, they should be involved in bond formation. So what we should do is we have to construct group orbitals by considering all the sp3 hybrid orbitals. That means these sp3 hybrid orbitals of water molecules, the 6 water molecules, You have to consider the sp3 hybrid orbitals of these 6 water molecules which are approaching along the 3 coordinate axis. Can you follow this? So these 3 water molecules, they are approaching along the 3 coordinate axis, and these are the orbitals which should be considered. Now we have to construct a group orbital that should have matching symmetry with which orbital? With the s orbital. First of all, we have to construct a group orbital which should have matching symmetry with the s orbital of the metal. Now you know that the s orbital, it is spherically symmetrical, isn't it? It is spherically symmetrical. So this is the s orbital. If we consider that the phase is positive, so we can say the phase is positive throughout. Um, the phase is positive throughout, suppose. Then how can these six orbitals be used to construct a group orbital having matching symmetry with this s orbital? Very simple. If you consider that, see, if এইটাকে আমরা পজিটিভ নেগেটিভ রাখছি, পজিটিভ নেগেটিভ, পজিটিভ নেগেটিভ, এই সাইডে পজিটিভ নেগেটিভ, পজিটিভ নেগেটিভ, পজিটিভ নেগেটিভ. See, these 6 orbitals, they are combining together, and if you look closely, they will have matching symmetry with this s orbital. It will have matching symmetry with this s orbital. That means these 6 atomic orbitals, they are linearly combined to form a group orbital that have matching symmetry with the s orbital, outer s orbital. তাহলে এটার নাম যদি আমি সাপোজ phi 1 দিই, x axis বরাবর, এটার নাম দেওয়া হচ্ছে phi 2. Suppose this is phi 3 y axis, along the y axis this is phi 4, phi 5 and phi 6. Then we can say that phi, say this is the this is the wave function. These are the wave functions associated with the sp3 hybrid orbitals, and let phi be the wave function associated with this group orbital. Now, since this group orbital has matching symmetry with s, we can name it as phi s, and we can write it like this with a normalization constant. I think instead of writing s, we should say, instead of s, we should say a1g. See, this has matching symmetry কারণ s টাকে তো আমরা already বলেছি transforms to a1g. So psi a1g করি আমরা, phi a1g. So this is n a1g. This is the normalization constant, and we can write like this: phi 1 plus phi 2 plus phi 3 plus phi 4 plus phi 5 plus phi 6. So this is how we can construct the group orbital LGO. This is the LGO having matching symmetry with this S or A1G of the metal center. So we have constructed the A1G, we have constructed the LGO having matching symmetry with A1G of metal. Now what we want to do is, we have to construct group orbitals. So we have already constructed the group orbital having matching symmetry with A1G. Now we need to construct the group orbitals having matching symmetry with T1U. See, there are 3 orbitals here. So we need to construct group orbitals having matching symmetry with T1U. How is it possible? Suppose if you look at along the 3 axes, now if you consider these 2 orbitals, এটা x, y and z axis. This is the position of the metal, obviously. And you know that this is phi 1, phase-টা যদি আমরা এরম দিই, and in phi 2 if you reverse the phase, that means এটা negative, এটা positive. See, in our previous example, this side was positive, this side was negative, and that's why we named it as phi 2. But in this case, we have just reversed the phase. So we should name it as minus phi 2 because the phase is just reverse. So this group orbital, if you look carefully, it has matching symmetry with which orbital? It has matching symmetry with px, isn't it? So we can write like this: the phi of px, this will be n of px into phi 1 minus phi 2. In a similar way, phi py, it should be n py into, দেখো along the y axis যদি হয়, it should be phi 3 minus phi 4 along the y axis, and phi pz, this is n pz into, দেখো along the z axis, phi 5 minus phi 6. So these three orbitals, these are actually T1U LGO. So we have constructed the group orbitals having matching symmetry with T1U of metal. Okay. Then we have to, so what we have done is, so we have done both these. একটা হচ্ছে A1GO করে ফেললাম, T1U. We have constructed the group orbital. Now we will move to construction of group orbitals having matching symmetry with EG. We are just omitting T2G for simplicity right now, because T2G orbitals, you'll find that, I'll explain it in my next class, that these are involved in pi bonding. Currently we are considering sigma bonding only. So that's why we are omitting this T2G. We are coming to EG set. So in a similar way, you can construct group orbitals having matching symmetry with EG. So EG, you know that these are the two orbitals, dx square minus y square and dz square. These are the two orbitals which transforms into EG set for the metal. So if you want to construct the LGO, say corresponding to dx square minus y square. So how to go ahead? See, these are the axis. This is the z axis. This is the x axis. So these are the orbitals which are involved in bond formation along the x and y axis. তাই তো, এটা হচ্ছে x, এটা হচ্ছে y axis আছে. So these are the orbitals which are involved in bond formation. This is the position of the metal. Now if we know that the shape, if you look at the dx square minus y square orbital, this is the shape of dx square minus y square. If you remember, dx square minus y square, this is the shape of dx square minus y square, where if this is in positive phase, this should also be in positive phase, and the other two, these two, they will be in negative phase. So if this is in positive phase, this should also be in positive phase. So the other two lobes, they will be in negative phase. So we can construct the group orbital like this: positive, positive, negative, negative. This one will be negative, this one will be positive, this one will be positive, this one will be negative. Now if you look carefully, this is what? this is phi 1, this is phi 2, this is minus phi 3, and this is minus phi 4. So the group orbital LGO having matching symmetry with this one. Okay, the LGO having matching symmetry with this one. Say we can write like this. Say phi dx square minus y square. This equals n dx square minus y square, normalization constant. So phi 1 plus phi 2 minus phi 3 minus phi 4. So in this way, we have constructed the LGO having matching symmetry with dx square minus y square. Similarly, for dz square also, we can construct the group orbital. Um, it's like this. See, dz square, it can be considered to be made up of two orbitals, dz square minus x square and dz square minus y square. So it can be considered to be made up of by linear combination of these two orbitals. So that means dz square minus x square কিরকম দেখতে হয় দেখো, এই dz square minus x square, এই z are x-axis, this is the y-axis, and dz square minus y square. So this is dz square and dz square minus y square. So we can write like this. Now if you combine these two, so this is x, y, and z axis. Now if these two orbitals are linearly combined, then we get this dz square orbital, which is a combination, which is a linear combination of these two atomic orbitals. Often you'll find that দেখো ফেজটা দেখো কিরকম হচ্ছে, ফেজটা you can well understand that যদি আমি lobes গুলোকে পজিটিভ রাখি এইরকম, and you know that there is a torus of electron density along the xy plane, এবং এই টোরাসটার ফেজটা আমরা নেগেটিভ দিচ্ছি বিকজ xy প্লেনেতে যে ফেজটা আছে that is negative. So this is the x-axis, this is the x-axis like this, and the y-axis x, y, and this is the z-axis like this. So dz square orbital, we can consider it to be a linear combination. It can be considered as a linear combination of these two orbitals. Okay, so from this we can construct the group orbitals for dz square also. I'm not going into further complications. Just I'm telling you from this idea, if you can look at Hui's book or any other normal textbook, you'll find it is properly written over there. I'm not going into further complications. So in this way, we will be able to construct group orbital having matching symmetry with dz square. So dz square and dx square minus y square orbitals, we have, if we can draw the group orbitals, rather ligand group orbitals, so they should be termed as what? EG-LGO. EG-LGO. So that means what we have done as of now is we have constructed group orbitals having matching symmetry with this, this, and this. Now what we will try is we will try to draw the energy level diagram. ঠিক আছে? So we shall try to draw the energy level diagram now. So Now let us consider the metal to be in this side and so আচ্ছা মেটালটা আমরা জেনারেলাইজ যদি করি সাপোজ if it is uh, nd, তাহলে d orbital, you know these 5d orbitals, they are degenerate. Now if you can write this degenerate set of orbitals like this, they are degenerate, they have the same energy. Okay, so we are writing these d orbitals. These are n minus 1 d orbitals. So these 5 n minus 1 d orbitals, we will say that these are degenerate. Okay, now we can name them also. So these three, we have named them as what? These are T2G, DXY, DYZ, DXZ, and these two, they are EG set, DX square minus Y square and DZ square. Okay, let us write it. DXY, DYZ, DXZ. So these are the three orbitals, and EG set means DX square minus Y square and DZ square. So these are the orbitals, but we have divided them into symmetry groups, T2G and EG. These are the symmetry groups, but these orbitals, they are degenerate. Next, if you consider the next orbital, it should be NS orbital. So this is NS and it transforms to A1G. Right? So this is the NS orbital. And the next orbital, it should be NP, NP orbitals, PX, PY, PZ, isn't it? So these are the three degenerate PX, PY, PZ orbitals, which has transformed to what? T1U. So in this metal, so for this metal, we know that these orbitals, they actually transform to 4 symmetry groups. Now if you look at the ligand group orbitals, LGO, so we have already constructed the LGO, we need to show them in the energy level diagram. And for simplicity, okay, for simplicity, we are considering the LGOs of more or less same energy. This is for simplicity. So which are the orbitals which we have shown? A1G, A1G. Next we have shown T1U, and also we have shown EG. So we have considered them to be of practically similar energy, the LGOs. Okay, so the energy should be slightly lower than that of ND. It should be slightly lower. Now we have to combine these orbitals. Combine কার সঙ্গে কার করব? দেখো A1G will combine with A1G. This one, of course. A1G will combine with A1G. So these two will combine and they will form a bonding molecular orbital and an anti-bonding molecular orbital. Okay, so let it be A1G. Obviously the symmetry will be A1, A1G star. So these two will combine to form these two group orbitals. This A1G LGO and A1G of metal, they will combine to form these two orbitals. Okay, next the T1U. See, the T1U orbitals, if you look at this T1U orbitals, this one, This T1U orbital will combine with this T1U, isn't it? To form a BMO and a ABMO. So দেখো এই ABMOটা আমরা এখানে দেখাচ্ছি, সরি, দিস ABMO কিরকম হচ্ছে দেখো, আর BMO, so they have combined to form BMO and ABMO like this. So we can name them as T1U and T1U star. T1U and T1U star. Okay. Then look at this EG. The EG set of orbitals. If you look at the EG set of orbitals, see this EG and this one. A EG ta or A EG ta, they will combine once again to form a BMO and a ABMO, isn't it? So these two will combine. So this will be EG and this will be EG star. EG and EG star. And since we have not constructed the LGO having matching symmetry with T2G, for simplicity, we have not drawn because it will be involved in pi bonding. So these three will remain as non-bonding. So T2G non-bonding. So this is the এখানে যে ছটা লিগ্যান্ডের LGO করছি, this is ML6, this is the molecular orbital energy level diagram. Now try to understand each of the ligand, they donate a pair of electrons. They donate a pair of electrons. So each of these ligands, see there are 6 orbitals. Each of these 6 orbitals, they will contain a pair of electrons. Okay. Now if you look at the nature of these orbitals, which will have ligand character, more ligand character, which will have greater metal character. See, this will have greater ligand character. This will have greater ligand character. This will have greater ligand character because this is of slightly lower energy. Greater ligand character. Now this is of more metal character. More metal character. Metal character. And also this one is also of practically metal character. Isn't it? Now if you start filling up the orbitals, see there are 6 ligands which are donating 12 electrons. Now 12 electrons, they will be accommodated like this. Look carefully, 1 2 3 4 5 6 7 8 9 10 11 12. So these 12 electrons, they are donated from the ligand side. So this is basically formation of 6 bonds, donation of 6, I mean the ligands, they are donating electron pairs, sigma donation basically. Now if you look at this gap, if you look at these orbital, this is non-bonding. If you look at this orbitals carefully, so this is T2G non-bonding and EG star anti-bonding orbital. Both are of metal character. Now if you compare this with our previous diagram, previous simplified diagram. Okay, if you compare this with our previous simplified diagram, look, non-bonding, anti-bonding orbital, both are of metal character, and this gap is del O. এই যে non-bonding and anti-bonding orbital of metal character, this energy gap is del O in the molecular orbital theory. So when we are considering this octahedral complex, if you look at this diagram, the energy gap between the non-bonding and anti-bonding molecular orbital of metal character, we can say this is del O, isn't it? And if you look at crystal field theory, we have already mentioned in crystal field theory, if you remember, this was T2G and EG, and this was del O. And in crystal field theory, we have considered the orbital of the metals only, and the electrons of the metal centers, these suppose if it is a D5 system like this. For example, MnH2O whole 6 2 plus. Manganese 2, you know, it is a D5 high spin system, isn't it? So in crystal field theory, we write like this, D5 high spin. And in molecular orbital theory, we will write like this. That means what we are trying to emphasize is that if you compare this portion of molecular orbital theory with crystal field theory, this one, the results are same. That means that is why you see crystal field theory and molecular orbital theory, they are giving similar results as far as sigma bond is concerned. So in crystal field theory, we have considered only point charges. In molecular orbital theory, we have considered the orbitals of the ligands. But you see, this portion becomes comparable with this portion. That is why this is correct. And since this is correct, crystal field theory gave correct results. Although the theory is not meaningful. Point charges, ligand should have dimensions, it should have orbitals, which should combine with metal orbitals. In spite of that, we got, CFT gave good results. CFT was able to explain many properties of coordination complexes. The reason is this portion is similar. Okay, so with this basic idea, we will further move to pi bonding in molecular orbital theory in the next class.